So today, Tudor Padurariu from the University of Bonn will give his last lecture of his mini course on BPS cohomology and quasi-BPS categories. Tudor, please.
Okay. Yeah. Thanks. Yeah. So we stopped in a certain point, but then there were several questions, so I wrote some answers at least to try to answer them as best as I can. So one was about wall crossing, and then one was maybe kind of more in the direction of motivation of why one looks at this window categories in the first place. So for the first one, this is kind of some version of wall crossing one might imagine. So if we have Q a quiver, and let's assume for simplicity that the potential is zero. I mean, one can also put potential in the picture, but coha of X will be the following: Ni times Z graded vector space built out of singular cohomologies of XD. Then we can also consider a K-theoretic version of the whole algebra of Q. So here it's Ni graded, and we consider Grothendieck group of the category of coherent sheaves on XD, alternatively perfect complexes on XD. And there is also a categorical whole algebra. So it is a monoidal category, Ni graded, where individual categories are dbco of XD. And the Grothendieck group of this third one is the KH. So at least one version of wall crossing is as follows. If we consider a stability condition theta, we can also define other whole algebras that kind of consider just objects semi-stable with respect to theta of a fixed slope. So I denote them by coha mu q. So this is the direct sum of singular cohomology of the stack xd semi-stable, where d is a dimension vector of slope mu.
So you allow non-strictly semi-stable
Yes,
mu,
yes,
which means that it's cohomology of a stack.
yes, yes,
okay.
yes, yes. And then one version of wall crossing is this one that I wrote. So, well, I mean, it's not obvious that it's wall crossing in this form, but it says that there is an isomorphism of graded vector spaces between coha of semi-stable objects for theta and of fixed slope and the full coha of Q. So wall crossing would mean maybe, kind of more standard form is to write this isomorphism twice for two different stability conditions. For example, separated by a wall. Okay, so if one considers this type of wall crossing, so kind of as a comment, so this wall crossing, this type of isomorphism follows from Harder-Narasimhan stratification. So it is geometric. One doesn't need to use any sort of new constructions or for this kind of magic categories or anything like that. Or one doesn't have to use intersection cohomology or this BBDG decomposition theorem. But kind of one remark here is that this is different from cohomological integrality that I discussed before. For example, if we look at the quiver with one vertex and L loops, there is no interesting wall crossing because there is no non-trivial stability condition. Because there are just two possibilities for GIT stability, determinant and determinant inverse. And in both cases, the open locus of semi-stable representations will be the full stack of representations of the L-loop quiver. So Yeah, so wall crossing, if we want to see what it says for the L quiver, yeah, there's nothing to say. Of course, there are versions if we frame the quiver and so on. But just in the shape, there is no interesting wall crossing theorem, but there is an interesting cohomological integrality theorem that kind of, again, splits this coha in terms of intersection cohomology. So for this version of wall crossing, there is a version of a similar statement in K theory, which is exactly the same. And one might ask for a version in for derived categories. Kind of the only one I can state, but I don't know, there might be better ones and a better understanding of what's happening here, is that this category, that's one of the graded pieces in the categorical whole algebra, has a semi-orthogonal decomposition where the summands are of this form. They come from non-stable locus. But there are infinitely many such SODs. Yeah, so there is no canonical one, as far as I see. Okay, so maybe a further investigation should. Yeah, I think it's worth investigating further wall crossing in this setting. But just even in this sort of primitive form at the level of categories, we know that there exists a semi-orthogonal decomposition. Maybe we don't know all of them or how they are related via mutations and so on. And it's also kind of not clear how two different SODs for two different thetas are related a priori.
So let me ask a question, maybe it's right.
Yep.
Of course, I mean, this semi-orthogonal decomposition, it's not about wall crossing, it's about rather existence of this BPS Lie algebra, because you or whatever you call the integrality, whatever, it's a presentation of coha as a graded vector space as a symmetric power of something. So it's not really about stability conditions, but there is this BPS Lie algebra, which kind of we predicted with Maxim and Davison and Meinhardt, I believe, constructed for quiver with potential. Is there a categorical version of this Lie algebra?
You mean of the Lie bracket?
Of the BPS Lie algebra, yeah, which is...
But the Lie bracket.
Yeah, Lie bracket, and also, as you know, its existence is due to existence of certain filtration on cohomology.
Yes.
Yeah.
No, I think, yeah, I mean, yeah, maybe a short answer, no.
Short answer, that's pity, because it's strange. It's a bit strange.
Well, no, I think no, as far as I know. I mean, I don't know how to construct it, but I don't think it's that strange, actually, because, or there are versions of, let me see. No, okay, so I think at categorical level, in full generality, that is in the generality of a symmetric quiver, let's say, or symmetric quiver with potential, or triple quiver with potential. I don't know how to do it. But in some examples, some big, easy examples where you have a finite type quiver, type A, and then I can write this quasi-BPS categories explicitly and see their generators explicitly. There are alternative ways. But I think there is an important difference between coha and keha, in that coha are half of Yangians, and inside the Yangian you have the Lie algebra. Lie algebra G inside the Yangian of G. And this is the BPS Lie algebra. But it's not the case for quantum affine algebras. For quantum affine algebra, you don't have the Lie algebra inside.
So if I remember correctly, you have a paper on this half algebra structure on K-hub.
Yes.
So does the half algebra structure give you the Lie algebra?
I don't think there is a Hopf algebra structure because it's completely parallel to the usual whole algebra business. You don't have, I mean, only for only if I remember correctly, only for categories, hereditary categories, homological dimension no more than one.
You are right.
The product and coproduct are compatible. And here, actually, it's an interesting question because I know there is this coproduct, which is not really the coproduct, it's meromorphic, it's something which I'm not sure that it's even compatible. So I don't know, Tudor. What's the
there
status?
Are several. Okay, so I think there are several questions. Sorry, just to say, I mean, for your first question, I'd hope that there is a categorical BPS Lie algebra, but I don't know how to construct it, and I kind of tried pretty hard in general. But
Yeah.
I think there might be sort of further ideas using this factorization structure in the case of -1 shifted cotangent stacks, global -1 shifted cotangent stacks that one may try. But indeed, I mean, short answer is I don't know how to see the Lie algebra, but it's also maybe a little related to what I said about quantum affine algebras. But about coproducts, there, let me see if I well, there are several coproducts one defines on a coha. There is a coproduct, basically, yeah, if you work maybe, let's say you work equivariantly with respect to a torus that scales the linear maps on the edges, and you also localize enough.
Yeah.
To kind of make your life easy, then basically, if you read the maps the other way, you can do that. And write formulas just as shuffle algebras, and then this coproduct is compatible with the product. And then the question is there, can you do this triple double construction? And you have a convenient pairing. Yeah, so
is there a pairing?
Yes.
With potential or without? Because for shuffle algebras you can do it directly, but for if you have
with potential, I mean, it depends. If you put some conditions in your potential, you can also involve the potential. So there is always a map from coha with potential to coha without potential, or kha with potential and kha without potential. Let me see, did I? Yeah, I think I didn't say. Yeah, it's just correct. As I said, there is a map, but it's not an inclusion. But the one way to make it an inclusion is to work equivariantly, maximally equivariantly, and localize. Okay, so this is a maybe brutal operation that maybe one does not want to do, but if one accepts this.
Yeah, localize means replacing the equivariant cohomology of a point with respect to the torus by a rational function.
Yes,
but
that's right.
When you do this procedure, what you say that there will be embedding of coha with potential to the one without?
Well, again, you need some. Now I cannot.
Well, potential should be also, I don't know.
Sure, equivariant.
Sufficiently good equivariant.
Yes,
yeah.
But for example, if you do the cubic potential from this triple quiver potential, that works.
Yeah, maybe. But in general, it would be strange.
Sure, in
because,
general, yeah. I mean, if you do a toric Calabi-Yau 3 beyond, maybe
yeah,
some
if
easy
something
example, yeah, then
three-dimensional, I don't know how you...
something generally three-dimensional, sure. Yeah,
Yeah.
what I said doesn't
Yeah.
work.
Okay.
So that what I said is maybe just some trick.
Yeah, all right.
Okay,
So
but
then
anyway.
kind of, yeah, so it's a good remark for the audience that wall crossing formulas, it's something which requires stability, and here we are talking about rather some analog of Poincaré-Bergov width, I would say, because you represent your whatever on the categorical level, your algebra is symmetric algebra of something. So then...
Yeah, but another remark is that this type of approach, this wall crossing, doesn't assume anything about the quiver Q. So I can take any quiver, can take the A2 quiver. But for cohomological integrality, I assume the quiver is symmetric.
Mm-hmm.
Yeah, so there are these two differences.
Is it kind of really a restriction, or you cannot do it in general? Or it doesn't, it is not,
No, it
it's
is.
not
It is.
true.
It is. You mean for symmetric quiver, this cohomological
For
integrality?
non-symmetric, you do not have this.
BPS enlargement.
You do not have it. Okay. All right.
Yes. Yes.
Okay.
Yeah. Yeah, but I think this question about this BPS algebra at the categorical level, I think it's very interesting. But I think it's genuinely hard. Or I think so. It's either false or either don't see a natural way to prove it, and then I think some more conceptual understanding is needed for general quivers.
You see, there are many hidden structures there. For example, the vertex algebra
Yes,
structure.
yes, yes. Okay, I agree. If one is in one of these cases when these categories are chiral, something like that, maybe. Yeah, but I still don't know.
Okay.
Okay, so then let me go back and try to motivate better the definition of this categories M delta. So they were defined using a certain polytope or using weight conditions from maps from the stack BGM into our stack of interest. So
but for historical reason, before you go to a concrete example, you motivated in this case. But in general, these Windows categories, who introduced them for the first time?
well, I think I think some of these ideas that appear in window categories. So some of these ideas that I will actually appear later in the proof that I'll give, or I'll try to explain how we prove this semiorthogonal decompositions. But I think this type of ideas go back to Telemann. But in physics, I'd say my understanding is that Horry was the first one to look at this great restriction rules.
But what was the idea? I mean, physicists, sometimes they kind of explain things in a more clear way. What was the point? For what reason? So you have a category, whatever, and is it important that there is a group acting somewhere? That it's kind of a JIT framework? Because in your definition, you use one parameter subgroups of stabilizers of points of stack.
Yes.
So, and then why Hori needed? I mean,
if I remember correctly, there is. Yeah, I actually don't know, but it's something to do with this F Fiat Ilianopoulou parameters. And then one varies them. And I think that there is some wall crossing that happens for some 2D theories. So if there are some 2D theories, and in one chamber they are described using, let's say, dB curve of some GIT. This is B side, dB curve of GIT quotient, and then when you cross a wall, you get some matrix factorizations.
Okay.
I actually don't know. I think
unfortunately Gabe is not here because he's an expert of this variation of GIT. Maybe he could comment.
Yeah.
Because I think it is used by rational geometers intensively. Yeah. All right. So anyway.
Yeah. Anyway. Yeah.
Yeah. Go ahead.
But I think in kind of also Ed Siegel, maybe in mathematics, after Hori's whatever paper
okay,
analyzed.
So if you see it for the first time, the question is why you need it, how it works, why you need to introduce some additional categories which depend on the weights of action, some one parameter subgroups, what it's kind of some intuitive picture.
Yes.
Yeah, all right.
Yeah.
Anyway, go ahead. Maybe it will be clear from.
Yeah. Okay. So let me try to motivate this construction. So let's work with an explicit example. So let's take this quiver. So it has two vertices, L arrows one way, L arrows the other way, and dimension vector 1, 1. So the gauge group is GM times GM, but the diagonal acts trivially. So I'll take the GM rigidification. So the representation space is a space of vector space of dimension L plus its dual with an action of now just one GM. So the group will act with weight 1 on the first sum and then -1 on the second sum. Okay, so what does cohomological integrality say here? Well, yeah, so it says simply that a singular cohomology of the stack decomposes as this BPS piece. Okay, we also gave it a geometric description using intersection cohomology, but this is actually not that essential for this example. Plus something that comes via the whole product, something that comes from parabolic induction. So something that comes from extensions, representations obtained as extensions from the one or dimension 1, 0 and 0, 1. Okay, so let's compute this. So the cohomology of the stack is polynomial in one variable Q. Then for this whole product, it is cohomology of B C star is also, this QH. And then when you do the whole product, you write the formula, you can compute it, and it's multiplication by H to the L. And it's the formula. So here, this P plus Q plus, what is this? Yeah, so there are kind of two whole products. So if we do extensions of 1, 0 by 0, 1, or vice versa. So they correspond to these two. So instead of taking multiplication via the whole product via this CL of weight 1, we could have taken it via the CL of weight -1. We would have gotten another decomposition. They differ just by a sign. Anyway, okay, so there are these two things. So cohomology of the stack and cohomology of the contribution from the whole product. And there is the BPS piece. So what is the BPS piece? In this case, it is canonical. So we know that cohomology is Z-graded. So this automatically tells us what this intersection, this BPS piece has to be. It's one-dimensional from 0 to 2L minus 1 in even degrees and 0 otherwise. Okay. So it's a graded vector space of total dimension L. Okay. What about K-theory? So how can we find the analog of this expression in K-theory? So we again start with Grothendieck group of the stack. We want to find question mark, and we want as its complement to have this whole product. Again, we can also, so this is for P plus, Q plus. There is also formula for P minus, Q minus that will differ by 1 Q%. Anyway, it's very explicit formula. So it's now this ring in Q plus minus 1, and this whole product is just multiplication by 1 minus Q at power L. So what is question mark now? The difference from cohomology is that there is no canonical choice. Okay, so yeah, okay, I don't know. It's just some, as our first guess, it will be just some space for which this equality is true. And there are, of course, infinitely many spaces. But we can maybe restrict our choices and look for it as the span of monomials in Q. And then it is still not canonical, but then there are these possible choices where you start with integer a, and then you take the span of these powers of Q. Q to the a up to Q to the a plus L minus 1. And this would give you an answer for question mark. So this is a first important difference. And this also has to do with this difference between affine algebras and Yangians. And so what I want to explain is that exactly kind of this construction of M delta is kind of this type of span. Yeah, so if you remember in this M delta, we had, we have this delta and we have some interval. And we allow representation with weights, with lambda weights for lambda, a map from BGM into our stack, in a certain interval. And the interval is specified by the cotangent complex. So in this case, it will have length L. And then we can move it in terms of delta. And this delta, this movement in terms of delta, is this A above. Okay, so let's kind of make this clear.
So you see, it's side remark, but maybe not quite side. In the theory of differential difference equations with singularities, you also have to make such a choice when you choose a monodromy. When you go from the, from monodromy, you go to logarithm. I mean, when you construct like, I don't know, Hodge filtration, so you have to choose a logarithm of the monodromy minus identity. You need to choose a nilpotent. So you need to make a choice which is similar to the choice of the of this interval which you mentioned. Either in this case some kind of a Q difference equations.
Yes, I hope. Yeah, I didn't work on this, but I believe there is.
Yeah,
I believe it's a close connection.
Okay, all right.
But I hope I'll understand this in future work.
Okay.
Yeah. So let's let's go back to the definition of M delta and explain that in this case recovers what I said. So that is the Grothendieck group of M delta recovers the above span. So M, the weight lattice is one-dimensional, and then we'll look at weights which are multiple of beta. Now we have a torus, so there is no condition on C. I mean, all weights are dominant. There is no rho, and we have this delta. So this is what we use to kind of move the polytope around. So this is a multiple of beta again. And we discussed this definition of M delta the first definition was combinatorial. It was in terms of a polytope. This is the polytope. in general is the Minkowski sum. It's half of the Minkowski sum of intervals 0, gamma, where gamma is weight of a V. And yeah, we need chi plus rho minus delta to be here. So what is this? Oh, I think I have a typo here. This is saying that C times beta plus 0 minus epsilon beta is in this interval. So we compute this interval because the weight beta appears L times in V, and minus beta appears also L times, because V is CL plus CL dual. Okay, so it's this explicit condition, explicit interval. So C, that specifies our possible weights is in a very explicit interval, and this is C. Yeah, this A from previous slide is just the C-link of epsilon minus L over. That is, so A in previous slide was this Q to the A. So the category M delta is the full subcategory of dB-co of the stack C2L quotient C star generated by line bundles O delta, where delta is C times beta, where C satisfies the inequality above. Okay. So now, what is our question mark? Going before, I mean, again, these are not all choices, and they may still seem artificial, but in any case. So we had this cohomology of this stack and this whole product, which was 1 minus q at power L times z q plus minus 1. And now we have these categories M delta, and the Grothendieck group will give natural a natural complement of the image of the whole product in the full category. But there are kind of maybe here we start seeing slightly more differences with cohomology. We also have this. We can also consider the image through the dual of CL. And the multiplication now differs by a power of q, not just by a sign. Okay, so this type of statement would be this version of cohomological integrality or PBW theorem for K theory. But then, what does this mean for derived category?
Yes. Question. So I thought to wait till end to ask. And in the slides 27, here the question is, how does the C star acting on the CL or C2L? It's just the scalar uniformly or have different direct sum of different weights.
It acts with weight 1 on CL and with weight minus 1 on CL dual.
Okay, I see.
Yeah, so it's this C star, it's just a C star at the vertex, the gauge group at the vertex.
So that weight 1 has a multiplicity L, right?
Yes.
Okay, thank you.
Yes, sure. Yeah, so what, okay, so in K theory we have this nice, have just direct sound decomposition. What is the version in dB-co? Well, in dB-co we cannot hope for just the orthogonal decomposition of categories. Sorry. So we look for semi-orthogonal decompositions instead. And then the results are that dB-co of the stack, C2L quotient C star, has semi-orthogonal decompositions where the summands are the category M delta and the categories dB-co of BGM of weight W. Yeah, so these categories, yeah, so if we take all weights W, it will correspond to this full K theory. Yeah, so recall this, that the category of coherent sheaves on BGM is just representations of GM. So it has an orthogonal decomposition in, where the every representation will split as a direct sum in representations on which GM acts with weight W. So now what am I seeing here is that there are many semiorthogonal decompositions of this category. There is no canonical one as above. And the summands are M delta, and this dBco of BGM of weight W can be embedded in dBco C2L mod C star in two different ways. So it can be embedded either via the CL with weight where C star acts with weight 1, or via CL dual where C star acts with weight -1. And this gives you many semi-orthogonal decompositions. So here I'm just, so some of them will be related by mutations. Some of them, I don't see how they are related by mutations. Because you cannot mutate infinitely many categories on the other side, but maybe, again, more conceptual understanding of this phenomena is needed, and But let me give you 3 types of semi-orthogonal decompositions that are not related by mutations. So of course, you can just, they will have infinitely many terms, and you can just take 2. You can take M delta and one thing on the right or on the left of M delta and move them. And when you move them, the thing that you move will still be a whole product. So this follows. So 3 decompositions are, if we want to find a version of this as it is written here. So for where one summand is M delta and the key theory of BGM is embedded in the key theory of the stack just via P plus and Q plus, then there is this SOD. So there is a semi-orthogonal decomposition with infinitely many terms. M delta sits in the middle, and there will be summands equivalent to dB of point for W less than some quantity here. And all the others for delta greater than this quantity will sit on the right-hand side. So here there is this kind of thing that might happen, that if epsilon minus L over 2 is an integer, then as you can see, we skip W. We skip exactly this integer. The reason is that this part of this whole product sticks to the category M delta, because in the definition of M delta, the interval we allow hits one more integer than it should. So it will have key theory of dimension L plus 1 instead of L. But if epsilon minus L over 2 is not an integer, then we kind of just have all possible W's, but some of them on one side, some of them on the other side. This is one SOD, but then there is again, as far as I can see, a different one, not related by mutation, where now we use P minus and Q minus. M delta will again sit in the middle, and there will be, it's written here. Yes. And finally, there is a third one, which is maybe not apparent initially in cohas, but one can also find analogs of this in cohas, where we mix P plus and P minus. We kind of sometimes choose, in the symmetric power, we sometimes choose the splitting 1,0 plus 0,1. Sometimes we choose it the other way. And this SOD has the feature, as opposed to the other ones, that M delta is at the end. So I should think a little. It's either right admissible or left admissible. Whereas it was not obvious, it is so from the previous 2 SODs. And now we pick half of the categories come via P plus and half come via P minus. Yeah, so this is kind of, again, it's not related by mutations to the previous ones as far as I can see, because you'll have to mutate infinitely many categories at the same time. Okay, so this is just to say that this type of SODs, and actually the one I mentioned in the theorem yesterday is the third one, but these SODs are the analog of this decomposition in key theory. Yeah. Okay. Yeah, so this is what I kind of prepared as answers for yesterday.
Before you move further, I mean, still, it's about this SODs. I mean,
yes.
they're categorical analogs of some, filtrations on the K theory, if you like.
Yes.
But what kind of filtrations these MDs? I mean, if you choose stability, then you can consider objects with a fixed Harder-Narasimhan type. You have maybe partial order on these, and you can speak about, filtrations by some subcategories with such that objects kind of for the quotients, objects belong to this semistables of given type, and what kind of these components, do they have geometric meaning, or they can be defined only in a formal way?
But in this case, I mean, for example, for decompositions 1 and 2, I think they have, right? I mean, they appear also as Harder-Narasimhan. So they actually appear as contributions of Harder-Narasimhan for this quiver that we considered. Where was it?
Yeah, you
and
have
with the
to,
non-trivial stability, you have two stability conditions, and they will give you as unstable loci either CL or CL dual.
Yeah,
so in
but
this case,
if it's just one quiver with one vertex and whatever else.
Yes.
And for example, no arrows at all. Do you require that L bigger than 0, or it can be 0 as well?
No, it can be 0. But then the category is just category of representations of the group, and it has an orthogonal decomposition.
I do not see a big difference between kind of 0 and 1 loops from the point of view of algebras, but for example, one loop, I don't know, Jordan quiver. So what can be a non-trivial semiorthogonal decomposition in this case? Because you mentioned previously
yes.
even if there are no stability, then
yes.
so these T structures, they come from what? Yeah.
It's direct product. Well, let me just write the formula, and then it's MDI WI I equals 1 to K, where we have sum of DI WI equals DW, and we have an certain inequalities. But we also know that this MDW is 0 unless W is D times N. In which case it is
What is N on
where N is integer.
Any integer. Okay.
And then in this case it is generated by O of N and this beta, the line bundle. Yes, so it will be this dB co of GLD mod GLD. W is generated by this MDI, DI and I, such that sum of DI and I is dw, and n1 is less than or equal to nk. Yeah, so all the summoned, they come push forward. Yeah, they are this GL products equals 1k GLDI times GLDI goes to parabolic. And then goes to GLD mod GLD. Yeah, so here on the Levy part, I'm considering a line bundle. So it's this.
Okay, hold
on.
Yeah. So.
Yeah, it's anyway, it's a line bundle. Anyway, I'm not sure what to write. So we take this line bundle and we pull it back to the parabolic and we push forward.
So is it the case of a quiver with one loop? Or?
Yes, this is case of quiver with one loop.
So we take, when you say parabolic, we consider what? We consider coherent sheaves or perfect complexes on these quotient stacks, which kind of go up in your on your slide with this monoidal or whatever, this convolution structure, and yeah, it's indeed it's some kind of parabolic induction, but I do not quite understand. All right, so maybe
well, I think so. Here
on.
it's I mean, a difference is that here, well, you could write the same diagram for L equals 0, and then you'll just have B, GL, DI, you know.
Well, cohomologically, if you do not do it categorically and do it at the level of cohomological whole algebra, then there is no essential difference between.
But I think there is a sign, right?
Yeah, there is a sign, but it's two periodic signs. So it's for even number of loops, it's the same. For odd number of loops, it's the same. Yeah, but this kind of decompositions, I'm just curious what categorically they
so if L equals 0, it's some kind of generation will boil down to some Borel-Delbot statement. But when L equals 1, it is this type of map. So that I wrote above. But this last map, let's see. So if it's Borel, it's B times B maps to G. So I don't know if you prefer this formulation.
I don't know. I don't know myself. It's still not quite geometric. But in order to finish this and move on, this L equals 0 or any even number. By the way, do you distinguish categorically between different even number of loops in this case?
Yes. I think they are very different.
So it's interesting and.
But I think also for Koha.
No, for Koha they are all the same for the same parity of loops.
I see, but I think, you still have this BPS space, and the BPS space depends on the number of loops.
Oh well. Yeah. Okay, yeah, I understand in this sense. But let me ask you this question. So the level of cohas, even an odd number of loops, they are related by some kind of what I called boson-fermion correspondence, but what is in fact causal duality. At the level of categories, do you see any causal duality? You already distinguish categories even with the same parity. That's
Yes.
already interesting. But is there some causal dual pairs for even and odd else?
Yeah, I think it's a good question. I don't know. I didn't think about it, but indeed, it's an interesting question.
Yeah. All right. Okay. Sorry.
Okay.
Yeah. Go
Yeah,
ahead.
yeah. So maybe yeah, just as a comment, I mean, did this type of map, yeah. So kind of did this last push forward this type of map, right? So if we replace, if we will work only with sort of the nilpotent cone, it will amount to T star. So for nilpotent cone, it will amount to kind of taking push forwards along this type of maps. So it is different from the case of L equals 0, where L equals 0 is just point mod B maps to point mod G, i.e. you just take push forward from flag variant. But yeah, I cannot say more.
Okay.
Yeah,
Okay.
so I think maybe I'm not sure what else to talk about. So
You're a speaker, I don't know. Yeah, you
yeah.
somehow illustrated this delta. Since kind of your time is limited, maybe there are some conceptual points which you would like to mention, because now you have 45 pages. Last time you have 35. So that, yeah.
I'm not sure.
Let
What can I
me.
say? I think, um, yeah, I mean, maybe there was this proof I wanted to explain, but maybe this is not conceptual. I don't know if it's
Proof is, yeah, maybe.
long.
Probably I should have asked you to give 5 lectures, not just 4, if I knew that in advance. Let's see, something I see about -1 shifted symplectic stacks.
Yeah,
What is it? There's semiorthogonal decomposition of matrix factorizations in
yeah,
terms of I don't know what. Ah,
yeah.
let's see. Terms of a category of singularities for these Windows categories.
Yeah, maybe I can talk about. Yeah, I have 6 minutes left. I can say something about this
And also there is
quivers that are not symmetric. Yeah,
yeah, maybe, yes. And
yeah.
also there is some last piece, representations of whole algebras, so people like representations of whole
Okay,
algebra.
but yeah, in 6 minutes. Okay. Anyway, I
I
think
don't know. It depends
yeah.
what if there is a theorem which can be.
Theorem. No, I think I just kind of discuss
All right, then
one
whatever.
example. Yeah.
Choose what you want.
Okay. I think one may one direction is we focus we until now we just discussed symmetric quivers, but one may ask what about other type of quivers, and an important construction even for symmetric quivers is that of framed quivers. So out of framed quivers, if we consider a quiver Q and a framing, we have a stability condition coming from adding this framing. And so we'll get varieties. And a feature is that the whole algebra, the coha acts on whatever theory, put coha, keha, or derived category of this moduli spaces of semi-stable framed representations.
When you say framed, your arrows go all in one direction?
Yes,
or...
yes.
Okay,
In this
okay.
case, yes, yes.
Yeah,
yes.
yeah, okay.
For example, here, let's say I'm just adding one. Usually, I would add more framings, but let's say here for simplicity, you add one framing. Yes, and then the stability condition is just that V generates, so the image of one under this frame map is a vector in CD, and CD generates, this vector generates the full space under the action of the L loops. Yeah, so this is an action. We can also discuss it, yeah, in terms of this monoidal category, the whole algebra acting on this DBCO on this graded category. And then one feature is that one might use the BPS quasi-BPS categories for the stack XD. This MD deltas. Okay, so maybe here. Yeah, so one might ask for analog of MD deltas for the frame stack. And there are certain constructions there as well, but they will output just what I wrote here, DBCO of XFD semi-stable. But we would like to maybe decompose it in pieces that come from the BPS part, quote unquote, the BPS Lie algebra. As I said, it's not categorical Lie algebra. This is what we'd like, but anyway. At the level of cohomology, it will amount to a decomposition of our representations in terms of pieces from the BPS Lie algebra. And indeed, this can be done. So there are sort of compatible semiorthogonal decompositions. So here I just illustrated by one example. So if we take the number of loops to be 3, yeah, so this space, this 3-loop quiver appears when describing moduli of sheaves supported on schemes of dimension 0 on A3. But it's one of these quivers we talked about, this L-loop quivers where L is 3, and it's one of these kind of rigid quivers where there is no stability condition. So we cannot do wall crossing. We can only do this SOD. But the frame version is this non-commutative Hilbert scheme. And this is kind of how the two SODs that I mentioned in this theorem above compare. So for the stack is the usual one, the product of these categories after decompositions, and where we have this slope condition. But if we include the framing, again, we have parabolic induction, whole product. Again, we have this condition, but then we need to restrict the slopes in an interval of length f, any interval of length f. So here I just chose 0 to f. And
can I see the f in your framing in the quiver case?
Sorry?
Can I see the f, the framing in the quiver?
So yes. So
you have a quiver go here. So now you corresponding to each f, you have a framing, right?
He considered the example.
Yeah. So f is this C. So I have a quiver. Yeah. I have a quiver with one vertex and 3 loops, and I add the framing, and then I add f arrows.
Okay. So the f is the number of arrows. Good.
Yes.
So that kind of corresponding to the highest weights.
I have to, okay, maybe.
Yeah, Nakatima's anyway. Construction of representations.
Yes, okay.
Right.
Yes.
Thank you.
It's not quite Nakajima.
It's similar. This is different, but the Nakajima quiver variety using that to give highest weight representations.
Yeah, but it's not a quiver variety, so I'm...
No, this is not quiver variety, but it's analog of that.
Yeah, anyway, I think, yeah, we have these SODs, and this type of SODs also hold after we impose potential. So for this triple loop quiver, yeah, we can also put the usual potential, which is XYZ minus XZY. So then we obtain a different semiorthogonal, semiorthogonal decompositions. So first of this category, this is some category of matrix factorizations whose critical locus is the stack of length B sheaves on A3. And by dimensional reduction, it's just it's equivalent to the category of coherent sheaves on the commuting stack, i.e. the stack of length B sheaves on A2, and has some SOD in some categories we described. And then this theorem also gives you an SOD of this category of matrix factorization whose critical locus is the Hilbert scheme of points on C3.
Sorry.
And then if you...
what acts on what? I assume that something should act on the category associated with the Hilbert scheme. So
yes, this
should act, all right.
Yes.
Which is, yeah, I understand. At least at the level of cohomological whole algebras, I certainly understand. And go down. So what did you... you added the framing, which comes from this CD.
Yes.
Right. And discrete means what?
It's just a name, a simpler name for matrix factorization.
So
it's just notation.
It's Orlov, this category of singular. Okay, so all right. Yeah. Okay. Go ahead.
Yeah. Anyway, I think I'm out of time anyway. So
no, but you can finish because you said something about compatibility of semiorthogonal decompositions and.
Yeah. So the compatibility is this one that in this case this stack DB of the commuting stack has SOD in these categories. TI, WI.
Which again, you cannot describe them geometrically.
Yeah, we can. In this particular case, we can. But
and
yeah,
what they are, I mean, it's just.
Yeah. So in this case, they are basically DB of C2 epsilon. So this is C2 times an exterior algebra in one generator. Times n mod sigma n. Where n is the greatest common divisor of the n number.
All right. And you said that there is another compatible semiorthogonal decomposition.
Yes, so compatible, I meant that the stack DB CD has this type of SODs in this product of these categories, with these two conditions. And for this representation, we have same summands. The first condition is the same. This is the same, but we also restrict actually the number of pieces here. So this is what I meant by compatible. So they are compatible via the pullback map.
So in some sense, maybe Zhongzhu is right. It's sort of a weight type of restriction. It's still something. Yeah, all right. And at the level of algebras, if I go to periodic cyclic homology, I have what? Coha of
I think that
it's I mean, it's the simplest possible. It's two-dimensional Coha of
it's the Yangian of GL1 hat. you'll get the action of half of the eigenvalue of GL1 hat on a representation built out of this vanishing cohomologies from Hilbert C3D.
Yeah, okay.
So I think it's
Which is
this
sort of
kind of
toy
McMake
model. I
representation.
mean, the simplest possible case of this AGT story proved by Schiffman and Vassero at the cohomological
I think it's a little different because they look at representations of the same algebra we mentioned on Hilbert scheme of points on C2.
Yeah, so you're right, and you cannot make a dimensional reduction on C cube side along the one
Yes,
direction.
yes,
You
yes.
cannot.
No,
Yeah,
you cannot.
strange, because I wanted to ask you about the categorical version of this AGT conjecture.
But what do you mean? So by AGT conjecture,
By
you mean the
AGT,
actual AGT
I mean
conjecture?
several things. So
Yeah. Okay.
I mean it's already discussion, so I can. So I mean the action at the end of some kind of a vertex algebra on the cohomology of this moduli stacks of framed of instantons, which means some framed sheaves indeed on C square, not on C cube. You're right. But yes, it's a bit.
But you want a categorical action, let me see. So
Yeah,
you
I
want some sort
want
of
the category.
you want a category whose Grothendieck group is a W algebra. And this category acts on
W1
the,
plus infinity in your case, probably, yeah.
but I
Because
think
it's
also in this, like if you do higher rank sheaves on surfaces, like on
yes.
P2 framed, I think you get WGLR, right?
Yeah,
I
for
think
higher
you
rank
have,
GLR, yeah, but it's
uh,
still everything, if I remember correctly, our own work with Rabchak, Yang, and Zhao, it's all quotients from W1 plus infinity, this R.
yes, yes, yes.
Yeah. So then there is some huge base vertex algebra, but it's a question which in the other framework people do geometric representation theory, like categorical action of something on something else by whatever correspondences here.
Yes, yes,
And after all, it's a categorification of a positive, what you're doing, categorification
yes,
of a positive part of some quantum group
yes, yes.
in this
Yes. So
example.
if you want the categorical action of the whole algebra, pre-projective whole algebra of a quiver acting on dB-co of Nakashima quiver varieties, this can be constructed.
Yeah. Yes, at least this. Yeah,
Yes,
at least
at
this.
least this. Okay.
Yeah.
Yes.
Okay. So you
But you also want lowering operators, maybe.
well, lowering. Well, in this AGT story, there are two things. One is pure geometric, like in your story, exactly.
Yes.
But the other half, it's also essentially geometric, but it's like, you have the same algebra and you construct two different representations by lowering operators and by
Yes.
raising
Yes.
operators. So,
Yes.
and then you look what these two representations generate in your space. Yeah, so at least this, but I believe it's doable. But indeed, you need some analog of the involution in the story, but also in the actual AGT, you need an action of the vertex algebra, and this is done by hands. both
But
by
by vertex
Schiff.
algebra, you mean it's the W algebra?
Yeah, W algebra. In this case,
Oh.
rank R instantons, it's W GLR.
Yeah. But by hand is
By hand mean it's not
you
geometric,
just
at least it's not geometric. They construct, they and we, whoever, we construct some kind of free field operators which do
yes.
not have clear, at least for me, clear geometric meaning.
But would
And,
it have to do with something like
yeah, and I checked, you see, there is another direction which is sort of perpendicular AGT when you start with the quiver and construct representations of this quiver in coherent sheaves on surfaces.
yes,
Like even
this
on
quiver
C-square.
W algebras.
Quiver,
It's quiver.
exactly, yeah.
Yes.
And they have sort of analog of this AGT story, and it
But
goes
who?
exactly with the
They
same problem.
But they means who? Like Pestun and
They,
Kimura?
I mean, yeah, Kimura and Peston for the first time, and then Kimura still continues. He has written. Yeah, but at least I looked at the first papers, kind of couple of, and there is a geometric part which is action by correspondence. But then they construct what they call screening operators, again, pure algebraically using free field. And so that's kind of, it's a bit mysterious. But maybe I do not understand some important thing, but because this free field, it's not entirely non-geometric, but it's related to description of the set of the fixed points of the torus action on the moduli space of instant. It's kind of a product of Hilbert schemes, but the very action is kind of by formulas, and so that's something which maybe people already kind of worked it out, but I missed that development. All right, and it would be nice to have these geometric actions which people with like
I did
Kakautis, since you are working with him now, you can ask him.
Yes.
Yeah.
No, I think it's a very good point. Yeah, it would be great to have.
Yeah. I mean, it's very interesting. I wish you spoke more, but okay. More questions today. The last lecture, so it's your last chance to ask something.
Yes, I have tons of questions.
No, you don't have time for tons of questions.
Okay, I'll ask one question.
Yeah.
So far, in most of your example, you are using Jordan quiver as an example, and also your quiver is symmetric. So, as far as I know, that your collaborator Bu has worked with a quiver which is not symmetric, but kind of anti-symmetric, considering the symplectic and orthogonal cases. So my question is, throughout your talk, how much of all this will adapt to that situation? So in this case, the GRN will be replaced by symplectic or orthogonal.
I'm not sure. Hopefully, as much as possible.
Somebody will have it done, right?
Well, I mean, we have a project going on with changing and Yukunobu, but it's very much in progress. So I cannot.
Okay, so you are considering that. You are considering that, right? You don't want to reveal.
Yes.
Okay. Good
Yeah, I mean, I don't know, in the sense that I think it's something that needs to be done. Yeah.
I mean, so I was curious about all this stack. In what sense, how smooth the smoothness, or in each
Sorry?
The stack and the corresponding, just for example, assume those are vector bundles or sheaves with with some forms attached on it. So, but the question is the smoothness of the stack. Is that automatic or from your instance?
I think it's. I mean, I'll need to kind of see exactly what example you're looking at, but usually, I'd say yes. I mean, for example, if you look at moduli of vector bundles on a curve, or you can change it to G bundles, where G is a different group that you might be interested in. They are both smooth stacks. And similarly, local models for GLD are given using quivers, but for different groups, they are not using quivers, but still they are smooth stacks with very explicit description, using maybe adjoint representation of your group, things like that, and they are still smooth.
Actually, Tudor quiver falls exactly into that picture, because there is only a single vertex, which is both symmetric and also anti-symmetric as well. And in that case, your setting, the GLN becomes this, whether it's a symplectic group or scaled symplectic group. So by adding a larger center to it, that in that case, the group will be called GSP, not just as SP, but as far as I see that you don't need, you are using the large center, you are using the center of GLD.
Yes.
A lot.
Yes. Yeah, it's a good point. It's a good. Yeah, I cannot tell you, but I think it's good to look more closely at this Jordan quiver from what you're suggesting.
Yeah. Okay, that's my only question. I'll probably I want to take too much time, because Yan restricted me.
Yes, I do, because otherwise it will go indefinitely, because I have also, as you can imagine, a lot of questions. Maybe we should invite Tudor in the future. Certainly we should, because you explain things, I mean, in a quite good and understandable way, but still I'm kind of struggling to understand the role of this Windows category. They appear, we have running project with Rio Fujita and Yaping and Gufang on the category of line operators, and Windows categories appear there in a quite natural way, but algebraic way, and kind of geometric meaning is not. Okay, anyway, well, I ask you to send me the final version of your notes, because you wrote something even today during the talk. Yes. And well, thanks for giving this lecture course, and I hope it will be useful not only for me and Zongzhu, but also for graduate students and whoever. Yeah, so it's a very active area with kind of a lot of interesting questions, problems, and projects by different group of people. Tudor is kind of in the first line of these researchers. All right, so if there are no more questions, well, thanks again, and
thank you,
and see you.
Thanks for having me.
Yeah, thank you.
Thanks.